Hey kiddos, welcome back. This video is sponsored by no one. Today we're doing proof by induction. It's kind of challenging and it may be confusing at first, but you're gonna get it. It's really not that bad once you get a feel for it. It's one of those things that you do a couple practice problems and you feel confident in it. So proof by induction is used when you have a given claim that is usually true for some all in, usually integers, where it's a statement that's saying this is always true no matter what you plug in or what you substitute. So the way that we prove that is this three-step process where it involves a basic step where you just show that it's true for the first case scenario. And then you say you have an assumption where you're like, okay, well, I'm going to assume that this claim is true for some kth term. And then the last step is actually the induction step where you show that, okay, if the kth term is true, then using some algebra and using the claim from the previous step, you show that it's also true for the k plus 1th term. The way this is usually described is the analogy usually done is dominoes, where it says, okay, the first domino pushes, falls over, starts the chain. And then you say somewhere way down the row, you're going to say, okay, well, I assume that a domino down here falls over. Not any one specifically, just any domino from the range. And then you take that assumption and you say, okay, well, if that domino falls over, then therefore the next domino falls over. Well, if you're able to show that and prove that, then that means that it must be true for every term in the sequence, or in the analogy, it must be true that every domino falls over, which means your assumption at the beginning is true. So that was long-winded, but hopefully it makes sense once we start doing some problems. Okay, so for our first example, we want to use mathematical induction to prove that 11 to the n minus 6 is a multiple of 5, where n is any positive integer. So this is what I was saying before. Like we have a statement that's trying to be claimed as true for no matter what you plug in for n. So what we do is we usually define it as some, this is the notation I see most often, as some like p of n. And we say that's equal to 11 to the n minus 6, which we want to be equal to some 5a, or whatever you want to call it, where in this case n and a have to be in the positive integers. Okay, so we start by doing basic step 1. So we need to show that p of 1 is indeed true. So in this case, p of 1 is the left side is obviously 11 to the first minus 6, which equals 5, which equals 5 times 1. So check. We have shown that it's true. The first case is true. Obviously, you wouldn't want to do proof by induction if the very first case doesn't work. So that's why it's the first step. So now our next step is we assume that for some p sub k, 11 to the k minus 6 is equal to some multiple of 5. I'll use b this time. Again, you know, trying to be good math students, make these claims of what these letters mean, where n and b are positive integers. All right, our last step is next, the induction step. It's the most important step. So I usually write step 3. I'll just write step 3. Induction. So we need to do the k plus 1th term. So that would be equal to 11 to the k plus 1 minus 6. Now we can't just assume that this is equal to some multiple of 5. We're trying to prove it. This is the prove step. So here is when we do a bunch of algebra. So we are always going to use our assumption in this step here. So let's see what we can do. We know we can change 11 to the k plus 1 as 11 times 11 to the k. So we know that's true. So now here's where we use the previous step. We know 11 to the k can be substituted in using this statement above. So what we're going to call it is 11. I think you can see from the above step that from our assumption step we can substitute in 5b plus 6. So equals. So we can distribute here. So that would give us, we'll just leave it as 11 times 5b and then plus 66 minus 6. So that could be written as 5 times 11b plus 12, where this is an integer, so this is a multiple of 5. So we have shown that if a kth term is divisible by 5, then the next term is also divisible by 5. So all that's left to do is, to be good math students, you just need to wrap it up and say some type of therefore sentence. You say, therefore, by proof by induction, 11 to the n minus 6 is a multiple of 5 for all n in the positive integers. And this last step just rounds out the proof. You always restate your claim using a therefore statement. IB wants this claim in it as well, so get in the habit of writing it down. Okay, next example. Next example is a formula we're familiar with, and we're going to prove it using induction. The formula is the sum of the first n terms of an arithmetic sequence. Okay, so just like last time, we want to define this. We need to define our P of n, and that is just the given formula. Great. So I'm just going to start writing this as step 1, step 2, step 3. So step 1 is our basic step. We want to show that P of 1 is true. So we start with our left-hand side, I guess. So that's just equal to S of 1. Well, that means the sum of the first one term, which is just U sub 1. Then we'll deal with the right-hand side. That would be equal to 2U1. Oop, nope. Sorry. That would be equal to 1/2, because n is 1 in this case, times 2U1 plus 1 minus 1b. Well, obviously that goes away, and then you're just left with 1/2 times 2U1, which is just U1. So left-hand side equals right-hand side. Check. Done with that. So, oh, come on. Sorry. So, let's start with step 2 now. So step 2, assume, it's always the key word, that P of k is true. So P of k, that would be sum of the first k terms equals k over 2, 2u1 plus k minus 1d. So that's our assumption. We're always going to use this step in the final step, step 3. So we need to manipulate the k plus 1th term. This is our induction step. So the k plus 1th term would equal the sum of the first k plus 1 terms. Well, let's think of that as a concept. So the sum of the first k plus 1 terms would be the sum of the kth terms, sum of the first k terms, plus the k plus 1 term. Hopefully that makes sense. Like this is the sum of terms 1 all the way to k, and this is just the next term. So logically that's equal to this. So reminder, you can't just, on this step, you can't just jump straight equal to this. You can't just plug in both sides on your assumption statement. You start with one side and manipulate it until it's equal to the other. So, just like I said we would, we're going to use the assumption step here because we know that this is equal to this from our assumption. Okay, so sorry for the abrupt screen change, but this one's going to take a little bit of time. So we know sum of the first k terms is equal to k over 2, 2u1, k minus 1d. And then logically about arithmetic sequences, stay with me here, that the k plus 1th term would be the first term plus k times the common difference. Like to go from the first term to the k plus 1th term, you would add the common difference k times. So now the rest of this is going to be a bunch of algebra. So let's see if I can get this done in 2.5 minutes. So let's start by distributing k over 2. So we would get ku1 plus k minus 1 over 2d plus u1 plus kd. So if you notice, we have 2 terms with u1 and 2 terms without, and actually have d in it. So let's go over here and combine and factor. So we have u1, and that would be times k plus 1. I factored out the u1 from both of these terms. And then I'm going to factor out a kd, because that's what these 2 terms have in common. And that would give me, let's see, k minus 1 over 2 plus 1. Okay? So let's combine that ugly fraction over there using common denominator. So that would give me, if I change 1 to 2 over 2 and add that to the previous fraction, that would be k plus 1 over 2. Okay, here you're asking yourself, okay, what do I do next algebraically? So the nice thing about proof by induction is you know what it should look like at the end. Like we know our end goal, like everywhere there's a k, there should be k plus 1, so it should look something like this. So you're asking yourself, okay, what do I do next to make it look like that? Well, we have this k plus 1 over 2 here, so let's factor that out from our next step. So if we factored out k plus 1 over 2 from both of these terms, now this is the hardest algebra step, you'd be left with u1, you'd be left with 2u1 plus kd. Like think about it, think if you distributed this into that, you would indeed get u1 k plus 1, so I didn't make anything up. But then if you notice, this is equal to this, so I did it. All that's left to do is to write your therefore statement.